In the last video, we discussed exactly what type of time your clock or watch keeps. So the way they're sort of made to make our lives convenient is they're made to read 12 noon when the sun is at the highest point in the sky. That's just the way clocks are designed. So for example, if you put your tube like this is not part of the lab that you did, but if you put your tube in the orientation like this and had the sun coming right through it on one day, when the tube orients all the way around, rotates all the way around once, and say it returns to more or less the same position, say right here on the next day, this tube will also point at the sun, and our clocks and watches are programmed to read 12 noon on both these occurrences. You could do that with your tube, and if you use your watch, you would read 12 noon both times. That's solar time, and that's what clocks and watches are programmed to do. Makes it convenient for our daily lives. But what we neglected in this motion model here of the sun rotating is we neglected that the Earth is also orbiting around the sun. We didn't say anything about the fact it's following this dotted line orbit, say, all the way around the sun. We just ignored that. You can't do that. Makes the model invalid. So what we'll do then is let's go ahead and put that information into our model now, because that's what your lab is about proving. So number 2 then, we can put the sun here again. Of course, that doesn't change. But all we have to do now is we can put the Earth right here, as we did before, and we can put a tube on it, the way you're doing. There's the tube mounted on the Earth, although it's hovering a little bit above it. What we'll do now is we'll let the Earth go ahead and make a little progress in its orbit around the sun, something like this. And when the tube returns to the position to see the sun again, it'll be oriented like this. So in this initial position right here, say on day 1, you see the sun, 12 noon. In this second orientation, the tube is also pointed to the sun, so it's 12 noon. And as you might know, of course, the difference between a 12 noon on day 1 and a 12 noon on day 2 should be exactly 24 hours. Oh good, our clocks and watches work the way we want them to. But what is this business with the star? You didn't use your tube to track the sun in this case. So here's the way it works with a star. We'll draw all the familiar objects once again, but we have to be careful of scale, and here's the way I'll describe this. If you draw the Earth here and the sun here, and that distant star that you track, say way over there, the scale here is kind of off because the star is very, 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 very far away. The scale doesn't do it justice at all, and so what I'll have to do is let me redraw it, just compressing everything a bit more. The scale will still be wrong, but I can do a slightly better job for myself like this. I'll draw the Earth like that, and I'll draw the sun very, very close to the Earth like that, so I can get a little more distance out to that distant star over there, the one that you tracked. So here's what we'll do. Let's set ourselves back up again. Here is the tube, and I acknowledge that the tube now is pointing directly at the sun, and so you'd see the sun's light, but just ignore the sun for a moment here, and suppose your tube was some high-tech Star Trek thing that could ignore the sun and only look at the starlight. I hope you'll agree that'll be pointing directly at the star. So in this orientation, your tube is pointed directly at the star you chose, the way it passed behind your string on night 1. But now, of course, the Earth keeps rotating and orbiting, and so we'll draw the Earth down here a bit, indicating that it's moving in its orbit around the sun, right? Path might look something like this. And when are you going to see that star again? Well, you'll see the star again the way you did on night 2 when the tube makes it to the exact same orientation as it was up here. Over here we can see the star, and over here, although the scale isn't going to work out, it never does the way we draw it like this, but as you sort of go, you'll also see that star as well. Maybe let's draw the star a little bigger, something like that. I apologize for this curved line and the fact I have to bend it up a bit, but it's impossible to capture the correct scale of the Earth, the sun, and a star on anything I can possibly draw. I would literally have to go to a drawing maybe that looked like that, this. There's the Earth right there. There's the sun right there. And then your star would be, say, way over there. This kind of thing might just work, but then we can't see anything. So I'll just draw it like this, and you have to apologize. Just imagine this star. Think for a minute as you're watching this video. Just think quietly yourself. What is 100 miles in this direction from where you're watching? So look off the right side of your computer screen that you're looking at. What's 100 miles away? What state? What city? What mountain? What is it? Well, imagine the star is there, very far away. Okay, the point is that when your tube rotates to this exact position again the next night, you'll see your star again. But wait a minute. In this configuration here, you're looking at your star. You haven't quite seen the sun yet. So what do you have to do to see the sun to synchronize with your clock time again? Well, you'll have to wait a bit more. You'll have to let the Earth rotate a bit more. And I'll do that in a slightly bluer color here. You have to wait until the Earth's going to rotate, go a little bit more in its orbit, so I'll displace it a bit more. But as it rotates, eventually your tube will point to the sun again like that, in which case you'll be able to see the sun. So the issue in this experiment that you did is what happens here is you see your star first in this timing bit here. And what I mean by star first is you'll see the star disappear behind your string before you'll see the sun. Now, I realize you didn't do anything with the sun in this lab, but remember, that's what your clock is tracking. So your clock would track the 24-hour time when you see the sun, but you saw your star first. So hopefully, you will see the star here in some time less than 24 hours. And the proof then that the Earth is actually orbiting is you'll now have to look at, let's say, how much time went by between the Earth being in this position where it was on night 1 and this position on night 2. How much time went by? Well, how are you supposed to know that? Well, think about it a little bit now. Is the time here that we're talking about, the times that we're talking about here, that are sort of involved in all this analysis here, are all going to be around 24 hours. Okay, so we acknowledge you're not going to quite see the star in 24 hours, but you will see the sun in about 24 hours, but they're all near 24 hours. And so 24 hours is, of course, about 1 day. So what's so special about this? Well, it takes 365 days for the Earth to do one orbit. So this 1 day here is something like 365th of a year. So what does this 365 days in one orbit have to do with it? Well, it turns out that sort of by coincidence, or to make everything simple here, 365 days is very close to 360. And why am I saying 360? 360 degrees, that's how far the Earth rotates in 1 day also. So if this distance over here represents 1 day going by, well, that's approximately 1 part in 360 of the Earth's motion through its orbit, or about 1 degree. So when you saw the star on night 2 pass behind your string, the Earth traveled another 1 degree in its orbit around the sun. That's kind of your proof right there that the Earth is indeed orbiting around the sun. Now, what about the time difference? Well, if we agree then that's about 1 degree, we know the Earth rotates every 24 hours, 360 degrees. That's just the Earth spinning around its axis. 1 day, 24 hours, it spins 360 degrees. If I just multiply that number by 60 minutes and 1 hour to do a little units conversion here, I'll get about 4 minutes per every degree. In other words, the Earth rotates 1 degree every 4 minutes. And looky over here, this is that 1 degree, the 1 part in about 365 of the Earth's distance around its orbit. That 1 degree will also correspond to the 1 degree you'll have to wait for the Earth to rotate between the time you see your star and the sun again. But we know seeing the sun again represents 24 hours, so seeing your star, you have to wait for the Earth to rotate 1 extra degree to see the sun, or at the time you see your star, you'll be 1 degree of Earth rotation off of 24 hours. So this time here should mean something to you in terms of the data that you saw, and that will be the proof that the Earth is in its orbit.